Okay, everybody, this is an example of how to use everything that we've done so far in this unit, asymptotes, x and y intercepts, derivatives, concavity, everything. So we are going to sketch the graph of f of x is equal to x squared minus x over x plus 1. All right, first thing, vertical asymptote, pretty straightforward, x equals -1. The second thing, the horizontal asymptote. For those of you that remember from the video that hopefully you've watched and did the questions, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote, which means we have a slant asymptote, and this is the same example I used in the slant asymptotes. You can look back to that, and we get y is equal to x minus 2. So 3 pieces of information already. All our asymptotes. Okay. Then we move on to intercepts. X and y intercepts. So we'll do x first. This is when y is equal to 0. So if you put y is equal to 0 into this, you get this. And if you remember from Math 12, you really only have to look at the numerator, because if this gets multiplied up there, what you would do to solve it, it disappears. So you have 0. We're going to factor out an x. We get x is equal to 0 and 1, which means our x-intercepts are 0, 0, and 1, 0. The y-intercept is when x is equal to 0. So if we put x is equal to 0, which is 0, which means we have a y-intercept of 0, 0, which you could have realized from that point right there, but that's okay. Good practice to do it anyway. Okay, now the calculus. We'll do that in brackets. That's always fun. What are we at here? 5. So we have to find, okay, we're doing it in blue, our critical numbers. Find where the maxes and mins are. Okay, so take the derivative. We're going to have to use quotient rule. If you remember, the quotient rule says the derivative of the top, which is 2x minus 1 times the bottom, plus 1, minus derivative of the bottom, which is 1 times the top, over the bottom squared. Now we just simplify. So we expand the top, 2x squared plus 2x minus x is plus x minus 1 minus x squared plus x. Okay, over x plus 1 all squared. Remember, don't multiply out the bottom, which is going to give me x squared plus 2x minus 1 over x plus 1 all squared. Okay, that's your derivative, first derivative. Critical numbers are what make it equal to 0 or undefined. So here, zero or undefined. Nothing is going to make it undefined because it's always a number plus this and then squared. Actually, well, I'm an idiot. What am I talking about? X equals -1. That's one of them. Wow. Sorry, people. X equals -1 makes it undefined. Now, the top, what is going to make that equal to 0? Well, you're going to have to use quadratic formula, of which I am not going to do. So you would essentially take this quad formula and it would spit out x is equal to 0, 4, 1, and negative 2.41. So those are all your critical numbers. You can do that on your own. I am not doing that. And on a test or a quiz or something, if we were in class, obviously I would give you something that factors. All right, now we're going to do second derivative because we have to talk about concavity. So 6, we got to find the second derivative. Okay, so this one actually works out nicely. So again, quotient rule, derivative of the top, which is 2x plus 2 times the bottom minus the bottom. I'm going to write this down here because this is going to get too squishy. Sorry, people. So we'll go over, go down here, give ourselves some room. So derivative of the top, 2x plus 2 times the bottom minus derivative of the bottom. So we have to use chain rule. Drop the 2 down. Inside derivative is 1, so we don't have to worry about it. Times the other function over the bottom squared. That's the 4. All right, now it's simplifying it. Factor out an x plus 1. Left with 2x plus 2. Okay. That cancels one of those. You have to 3. If you expand and simplify the inside, everything goes away, and I encourage you to do that. What you end up with is this. That is the second derivative. So we find our possible points of inflection by setting it equal to 0 or undefined. Again, the only one would be x is equal to negative 1. All right. So then we make our little chart, our little number line. And we mark our critical points, which were negative 1, negative 0.41, and negative 2.41. So negative 1, negative 2.41, and 0.41. Scale doesn't matter. Those are critical points, which will tell us information about f primed. And negative 1 is also a possible point of inflection. So I'm just going to put it in a different color for the possible point of inflection. And those are second derivative bits of information. So we can do those right away. You test either side of your possible point of inflection. Any number will do. So this interval, put 0 into it. If I put 0 into the second derivative, I'm going to get a positive number, which tells me we are concave up on that interval. Put a negative number here, negative 2. I'm going to get a negative number, which tells me we're concave down. So from negative infinity to negative 1, I don't want to be signed out. 14 minutes, okay, people. Go away. So whatever, finishing within 14 minutes. So we test the first derivative. All right, and we test the intervals. So any number smaller than negative 2.41, put into the first derivative. you will see you get a positive, so it's increasing. Any number between these two, -2 would be fine. You would see it's decreasing because it's negative. From here to here, -1 to 0 to 0.41, put in 0. You'll see it's decreasing again. Where's the first derivative? You put in a 0, goes away, negative over a positive. It's decreasing, it stays decreasing, and then on this interval, and a number bigger than that, it's positive. So negative, positive. Okay, so now we're going to sketch this graph based on this information. So these graphs are kind of tricky. Vertical asymptote at -1. Mark that. We have a slant asymptote of y is equal to x minus 2. So -2, up 1 over 1, up 1 over 1. Y is equal to x minus 2. We have, I'm going to start to use different colors because we have to mark our x and y intercepts. 0 and 1, 0. So 0, 0, this there, and 1, 0. This is 2. It's 1. Okay. We have a min at 0.41 because we go from decreasing to increasing. So 0.41, somewhere in there. We have a min. And if this is an x-intercept and this is an x-intercept, we know the graph crosses at that point. So we have a min. I'm just going to guess. We could calculate it. If you go f of 0.41 in your original function, it'll spit out the actual value. And we have a max at -2.41. So down here, we have a max. So the graph comes up, switches from increasing to decreasing to -1, and that's a vertical asymptote, so that makes sense. And then on the other side of the vertical asymptote, we are decreasing. We have to cross through our x and y intercepts. So we come down through our min, so that's 0.41 up, and then it starts to go along the line like that. And this is a really big graph. And that little point there is 0.41. This is a really messy graph, and I apologize. But if you punch that into Desmos, you will see the actual graph. Okay, so I have one question for you to do. It's not in the book, but you should graph y is equal to 3x to the fourth minus, that is your homework assignment question. To graph that, I want all pieces of information. I'll post the answer to it in a couple of days. Thank you.